Okay, step outside on a sunny day. Feel that immediate warmth on your skin even before the air around you heats up.
Yeah, instantly.
Or stand near a crackling fire. You feel the heat radiating outwards, right?
Yeah.
Not just the hot air
I
rising.
like feel it on your face, your hands.
Even holding your hand over like warm pavement or feeling the heat from a lamp without actually touching it, that energy is traveling through space.
It's reaching out to you.
Exactly, without needing a direct connection or any air to carry it. That fundamental way energy moves through the universe, from the heart of exploding stars to, well, the quiet cooling of a cup of tea.
That's thermal radiation. It's one of the big three ways heat gets around.
Right, conduction, convection, and this one. But unlike the others...
Yeah, this one's the champion of the void, right?
Yeah.
It works perfectly fine, even in the vast emptiness between galaxies where there's basically nothing.
And that's what makes it so crucial to understand, I think. It's not just some abstract physics thing.
Absolutely not. It's woven into our daily lives and like the whole fabric of the cosmos. Think about it, almost all our energy on Earth.
Comes from the sun.
Direct from the sun, yeah. And how does it get here? Through thermal radiation that's traveled millions and millions of miles through the vacuum of space.
So this deep dive is all about peeling back the layers of this invisible, powerful energy transfer.
We're going to explore exactly what thermal radiation is, dig into its core properties.
Investigate why different objects radiate heat differently, even if they're at the same temperature.
Right. And we'll meet the theoretical perfect radiator, the black body.
Ah, yes, the black body.
And trace the scientific journey, which includes some really revolutionary moments, actually, that led us to understand precisely how bodies emit this radiant energy across different temperatures and wavelengths.
Okay, so our mission today is to give you a really solid grasp of the core principles of thermal radiation.
Yeah, by the end of this, hopefully you'll see it everywhere in how your house stays warm or cool, in the color of stars.
And even in some of the most groundbreaking ideas in all of physics, apparently.
Definitely. So let's jump in. At its most fundamental level, what exactly is thermal radiation? We know it's energy moving through space, but what form does that energy take?
Right, let's unpack this. It's not conduction.
No direct contact, no bouncing vibrations through a material.
Not convection.
No movement of fluids like air or water carrying heat.
It's something else entirely.
It is. Thermal radiation is energy transferred by electromagnetic waves.
Electromagnetic waves, like light, radio waves.
Precisely. It's part of that whole family: visible light, radio waves, microwaves, X-rays, you name it. The difference is that thermal radiation is specifically the electromagnetic radiation emitted because an object has a temperature above absolute zero.
Because it's hot, or even just warm.
Exactly. At the microscopic level, the atoms and molecules inside any material are constantly, jiggling, vibrating and oscillating. And these vibrating charged particles, because atoms have charged parts, electrons and nuclei, they generate changing electric and magnetic fields.
Which then propagate outwards.
Yes, they propagate outwards as electromagnetic waves. And the hotter the object, the more vigorous these vibrations, the more jiggling.
And the more thermal radiation gets emitted. Makes sense.
So it's the jiggling bits inside creating these energy waves.
And you said earlier it's different because it doesn't need a medium, like air or water.
Absolutely.
Yeah.
This is its defining characteristic, really, and why it's so important for understanding energy transfer in space. Conduction needs something solid, liquid, or gas for the energy to pass through particle by particle.
Right.
Convection needs a fluid to flow and carry the heat along.
Got it.
Thermal radiation needs nothing. The electromagnetic waves just zip right through empty space.
Which is how the sun's heat reaches us across that huge vacuum.
That's exactly why. And it's also why, if you put a hot object in a perfect vacuum chamber, it'll still cool down. It radiates that energy away as thermal radiation. There's nowhere else for the heat to go via conduction or convection in a vacuum.
Okay, so electromagnetic radiation generated by temperature travels through free space. What other key properties should we keep in mind here?
Well, the sources we looked at highlight several key ones. First, as we said, it's electromagnetic radiation. Second, it travels through free space, no medium needed. Third, and this is a big one,
it
travels at the speed of light.
Wow, the speed of light. So it's incredibly fast, basically instantaneous for things here on Earth.
Exactly. When the sun emits thermal radiation, it takes just over 8 minutes to reach us, but that's because the distance is just enormous, right?
Millions of miles.
For everyday objects, the transfer is practically instantaneous. Okay, other important properties. Thermal radiation can be reflected.
Ah, okay. This is where shiny stuff comes in, like mirrors.
Yep. Think about a highly polished metal surface or those silver emergency
Oh
blankets.
yeah, the crinkly ones.
Those work incredibly well, not really by stopping airflow like regular insulation, but mainly by reflecting the thermal radiation your body is constantly emitting right back towards you.
So they stop your heat from escaping outwards.
Exactly. They are poor emitters of radiation themselves and good reflectors. It keeps your own heat in.
Huh. Okay, so it reflects. What else?
It can also undergo refraction, like when light bends as it goes from air into water.
Yeah.
Gamma radiation does the same thing if it passes from one medium to another with a different density. It's maybe less commonly talked about in basic examples, but it's a property it shares with all electromagnetic waves.
Okay. Reflection, refraction, anything else.
And finally, its intensity, how strong it feels, basically decreases with the square of the distance from the source.
Ah, the inverse square law. We see that with light bulbs too, right? The further away you get, the dimmer it looks, and quickly.
That's right, because it's the same fundamental kind of wave behavior.
Yeah.
Imagine the energy spraying out from a point source, equally in all directions, like an expanding sphere. As the distance from the source increases, that's the radius of the sphere, that same amount of energy gets spread over a larger and larger surface area, and the area of a sphere goes up with the radius squared.
So if you double the distance.
The energy is spread over an area 4 times larger.
Which means the intensity, the energy per unit area, drops to 1/4.
Exactly. Triple the distance, the intensity drops to 1/9.
That makes so much sense. It's why standing right next to one of those radiant heaters feels incredibly hot.
Yeah, scorching sometimes.
But just take a few steps back and it's way less intense. The energy is still traveling, but it's just spread thinner by the time it reaches you.
Precisely. So the core properties to remember. It's temperature-driven EM waves, travels in a vacuum, speed of light, reflects, refracts, and follows the inverse square law for intensity. These are really the building blocks.
Okay, so we know what it is and how it travels. But you mentioned earlier that not all objects radiate heat equally, even if they're at the same temperature. What makes one object better at throwing off this heat radiation than another?
Right. That's where things get really interesting, beyond just how hot something is. The material points to 3 main factors influencing the rate of emission. The temperature itself, of course, but also the nature of the object's surface and its total surface area.
Temperature feels obvious. Hotter things should radiate more heat, right?
Absolutely, and that's definitely the most significant factor. We'll see just how significant when we get to the laws later. But the surface properties, surprisingly important. And there's a classic experiment that demonstrates this beautifully, Leslie's cube.
Leslie's cube. Okay, tell us about this. Sounds old school.
It is, but it's brilliant. Imagine a hollow metal cube, like a little box. Each of its 4 vertical sides is treated differently.
Okay.
So one face might be coated with a really dull matte black paint, like lampblack. Another face is painted white. Maybe a third face has just ordinary paper stuck to it. And the fourth face is highly polished. Maybe it's silvered, or just buffed metal, really shiny.
Got it. 4 different surfaces, same box.
Exactly. Then you fill the cube with hot water. This makes sure all 4 faces are at the exact same temperature.
Right, the heat spreads through the metal.
Then you use a sensitive detector for thermal radiation. Traditionally, this was a thermopile.
A thermopile.
Yeah, it's basically a device that turns the heat radiation hitting it into a small electrical voltage you can measure. Think of it like a sensitive thermal thermometer that doesn't need to touch.
Okay.
You place this thermopile at the same distance from each face of the cube, one by one, and you measure how much radiation is coming off that specific face.
So everything's kept the same. The cube's temperature, the distance to the detector. The only thing changing is which surface you're pointing the detector at.
Precisely. And the results are really striking and always consistent.
Yeah.
The face coated with the dull lamp black. It emits the most thermal radiation.
The black surface radiates the most heat.
Yes. And the highly polished, shiny face. It emits the least. The white painted surface and the paper covered surface, they emit intermediate amounts. Usually the white surface is a poorer emitter than the paper or the black.
Wow, that's a really clear, direct demonstration. The nature of the surface itself has a massive impact on how efficiently an object radiates heat away.
It absolutely does. It tells us that matte, dark, maybe somewhat rough surfaces are generally excellent emitters of thermal radiation. Smooth, light-colored, shiny, polished surfaces are poor emitters.
And this property, how well a surface emits compared to some ideal standard, that has a name, right?
It does. It's called emissivity. We'll formalize that a bit later, but yeah. High emissivity for the black surface, low emissivity for the shiny one.
And can Leslie's cube also show the effect of the other factors, temperature and area?
Yeah, conceptually you could. While Leslie's classic demo really highlights the surface nature, you could repeat the whole thing with, say, boiling water instead of just hot water.
And you'd explain.
You'd find that the radiation measured from all the faces increases dramatically with that higher temperature. The black face would still be the highest, the polished the lowest, but all readings would go up significantly.
Okay, so temperature definitely boosts radiation across the board. What about area?
Well, you could imagine having two cubes, same temperature, same surfaces, but one cube is just physically bigger than the other.
More surface area.
Right. If you measure the total radiation coming off the whole cube, which is harder than just measuring from one face, you'd find the bigger cube radiates more total energy. The amount of radiation is also proportional to the surface area that's available for emission. More surface means more little vibrating atoms radiating energy outwards.
So the big takeaway from Leslie's cube and these factors is radiating heat isn't just about how hot you are. It's also about what you look like on the outside specifically. Your surface's nature and its area are key players right alongside temperature.
Exactly. And this explains so many everyday things, doesn't it?
Yeah, like why do people wear light-colored clothes in the summer?
Well, two reasons related to this. The white surface reflects more of the incoming solar radiation, which is thermal radiation from the sun. And importantly, it also emits your own body's heat radiation less effectively than a dark surface would. So it helps keep you cooler by both reflecting external heat and emitting less internal heat.
Okay. And what about radiators in old houses? They're often painted dark colors or sometimes have that sort of metallic bronze paint.
Right. The idea there is to maximize their emissivity, to make them really good at radiating heat out into the room efficiently. A shiny, polished radiator would actually be less effective at heating the room by radiation.
Huh. And things like engine cooling fins or on the back of electronics.
Classic example of increasing surface area. More area means they can radiate heat away much faster and keep the component from overheating.
It all clicks together. Okay, let's shift gears a bit. We've talked about how much an object emits. What about how objects exchange heat through radiation and eventually reach some kind of balance? You mentioned Prevost's theory.
Yes. Pierre Prevost, back in 1791. His idea, the theory of heat exchanges, was quite advanced for its time. See, back then, a lot of people thought heat was like a fluid called caloric.
Yeah.
It just flowed from hot things to cold things. And maybe that cold was even its own substance.
Okay, the caloric theory.
Prevost had a more dynamic picture. His fundamental insight was that all objects, anything with a temperature above absolute zero, which is everything, basically are continuously radiating thermal energy.
Wait, hold on. So even like a block of ice or my hand right now at room temperature, it's radiating heat?
Absolutely. It might be radiating a lot less energy per second than, say, a hot stove burner. But yes, its atoms and molecules are still vibrating because they have some thermal energy, so they're emitting electromagnetic waves.
Okay.
And crucially, at the same time, all objects are also continuously absorbing thermal radiation that's falling on them from their surroundings.
Ah, okay. So everything is radiating and absorbing all the time simultaneously.
Exactly. That's the key. So what we perceive as heating up or cooling down is just the net result of this constant two-way exchange.
The net exchange. How does that work?
Well, if an object is hotter than its surroundings, say, hot cup of coffee in a cool room, it radiates energy away at a faster rate than it absorbs energy from those cooler surroundings.
So more energy going out than coming in.
Right. The net flow of energy is outwards. And so the object's internal energy decreases and its temperature falls. It cools down.
And if the object is colder than its surroundings, like a cold drink on a warm day,
Then the opposite happens. It absorbs thermal radiation from the warmer surroundings at a faster rate than it radiates its own thermal energy outwards.
Yeah.
Because it's colder, its own radiation rate is lower.
so more energy coming in than going out.
Yes. The net flow of energy is inwards. The object's internal energy increases, and its temperature rises. It warms up.
And this whole process, this net exchange, continues
Until thermal equilibrium is reached. That's the state where the object's temperature becomes constant, because it's perfectly in balance with its environment's temperature.
Okay, equilibrium. But according to Prevost, everything is still radiating and absorbing even then.
Yes, that's the beauty of it. At thermal equilibrium, the rate at which the object emits its own thermal radiation becomes precisely equal to the rate at which it absorbs thermal radiation from its surroundings.
Ah, so the outflow equals the inflow.
Exactly. The net exchange of heat becomes zero. The object isn't getting hotter or colder anymore, but the radiation processes haven't stopped. They've just balanced out.
The example in the material, the box A inside box B thing, that helps visualize this.
Yeah, it's a great thought experiment. You have a small box, A, placed inside a larger box, B, and critically, there's a vacuum between them.
So heat can only travel by radiation, not conduction or convection.
Right. Let's say we keep the outer box, B, at a constant temperature, TB. Now what happens to box A? If box A starts out hotter, say TA is greater than TB.
It will radiate more energy than it absorbs from B.
Correct. So its temperature, TA, will start to fall.
And if box A starts out colder, TA less than TB.
Then it will absorb more radiation from the warmer box B than it emits itself. So its temperature, TA, will start to rise.
And in both scenarios, TA will keep changing until
Until TA becomes equal to TB. At that point, they're in thermal equilibrium.
and the radiation stops.
No. That's the key point from Prevost. Box A is still radiating energy towards B, and B is still radiating energy towards A. Box A is absorbing radiation from B, B is absorbing from A. But at equilibrium, when TA equals TB, the amount of energy A emits that gets absorbed by B is exactly equal to the amount of energy B emits that gets absorbed by A.
The rates are perfectly matched?
Perfectly matched. The net heat flow between them is zero, so the temperature of A stays constant at TB.
Okay, that clarifies the equilibrium idea. It's a dynamic balance, not a static stop. Now, there's this other cool little device mentioned, the Crookes radiometer, the thing with the spinning vanes.
Ah, yes, the Crookes radiometer. A classic physics toy, almost. It looks quite magical. It's a glass bulb with most of the air pumped out. Not a perfect vacuum, but very low pressure.
Okay.
Inside, there's a little spindle with 4 vanes mounted on it, kind of like a tiny windmill. And it's balanced, so it can spin very freely.
Right. And the vanes are special.
Yeah, each vane has one side painted matte black, and the other side is polished and shiny, like a mirror.
Black on one side, shiny on the other. And you put it near a light bulb or just in the sunlight?
And it starts to spin. Usually the vanes spin, so the blackened side is moving away from the light source.
Why does it do that? It's not the light pushing it, is it? Like solar sails?
Ah, that's a common misconception. It's actually more subtle and involves the thermal effects and the remaining gas molecules. Here's what happens. The thermal radiation from the light source hits both sides of the vanes.
Okay.
The blackened side, being a good absorber, like we saw with Leslie's cube, absorbs more of this radiant energy than the polished side, which reflects most of it away.
So the black side gets hotter than the shiny side.
Exactly, slightly hotter. Now, remember, there are still some gas molecules bouncing around inside that low-pressure bulb.
Okay, the residual air.
When one of these gas molecules hits the warmer, blackened side of a vane, it picks up more energy from the collision. It bounces off with more kinetic energy, more momentum, basically. It gives the vane a slightly stronger push backwards as it leaves.
Compared to hitting the shiny side.
Compared to hitting the cooler, polished side, collisions there are less energetic. So you get this tiny difference in the force exerted by the rebounding gas molecules, a slightly stronger push on the back of the black side.
And that adds up over the whole vane.
Yes, this differential momentum transfer creates a tiny net force, pushing the black side backwards, away from the heat source. And since the vanes are balanced on a low friction spindle, this tiny net force is enough to make the whole thing start rotating.
Wow. So the spinning isn't directly from light pressure, but from the thermal effect uneven heating of the vanes, causing uneven interactions with the leftover gas molecules. That's really clever.
It is. It's a beautiful demonstration that this invisible thermal radiation can be absorbed, cause a temperature difference, and ultimately lead to a measurable physical effect, like motion. It makes the energy transfer feel more tangible.
So the big takeaway from Prevost and equilibrium is that radiation is this constant give and take, and equilibrium is just when the giving and taking balance out. The net flow dictates heating or cooling.
Precisely.
Okay, we've covered what it is, its properties, the factors affecting emission, and this idea of radiative exchange and equilibrium. Now, let's dive into that theoretical ideal you mentioned earlier, the black body. It sounds perfectly black.
Well, yes and no. The name comes from the absorption property. By definition, a black body is an idealized theoretical object that absorbs all electromagnetic radiation that falls upon it. Doesn't matter the wavelength, doesn't matter the angle it comes in at, 100% absorption.
So if you shone a light on a cold black body, none would reflect. It would look perfectly black.
Exactly. That's where the name comes from. But the truly crucial property for understanding thermal radiation is what happens when you heat a black body.
Oh.
A black body is also the most efficient possible emitter of thermal radiation for any given temperature. It radiates more thermal energy than any real object at the same temperature.
Wait, so it's a perfect absorber and a perfect emitter. That feels weird. Usually things that absorb well are dark, and things that emit well are bright when hot. How can it be both perfectly black and perfectly bright?
It does seem counterintuitive at first, but it follows directly from the laws of thermodynamics and connects back to Prevost's and Kirshoff's law, which we'll touch on. Think about it. Imagine you had a perfect absorber that wasn't a perfect emitter.
Okay.
Now put it in an enclosure at some temperature, alongside a real object at the same temperature. If the black body absorbed perfectly but didn't emit maximally, it would keep absorbing more radiation from the surroundings than it emitted back.
It would get hotter than the surroundings, even though they started at the same temperature.
Yes. Energy would spontaneously flow from the cooler surroundings overall to this imperfectly emitting black body, making it hotter. That would violate the second law of thermodynamics. Heat doesn't just flow from cold to hot on its own.
Okay. So to avoid breaking fundamental laws, if something is a perfect absorber, it must also be a perfect emitter when heated to stay in thermal equilibrium.
Exactly. The ideal of perfect absorption necessitates the ideal of perfect emission. They're two sides of the same coin for a black body.
But it's theoretical. Do black bodies actually exist? How do scientists even study this ideal thing?
Good question. No real object is a perfect black body. But physicists came up with a very clever and highly effective approximation of one. A hollow cavity with a tiny hole in it.
A box with a hole. How does that work?
Imagine a box, maybe made of metal. The inside surfaces are deliberately made rough and are coated with something very absorptive, like lamp black or special black paint. Now drill a very small hole in one side of the box.
Okay, tiny hole into a black-coated box.
Now think about a ray of radiation light, infrared, whatever that happens, to go into that small hole from the outside.
It goes inside.
And what happens? It hits the back wall. Because the wall is highly absorptive, maybe 95, 99% of the energy is absorbed right there. A tiny bit reflects.
Okay.
But where does the reflected ray go? It bounces off and hits another inside wall. Again, most of its energy gets absorbed. Maybe a tiny bit reflects again.
And it keeps bouncing around inside, losing energy with each bounce.
Exactly. And because the hole is so small compared to the internal surface area, the chance of one of these multiply reflected, weakened rays finding its way back out through that tiny opening is incredibly small.
So essentially, any radiation that goes in the hole gets trapped and absorbed inside the cavity.
That's the idea. The hole itself acts as an almost perfect absorber. It doesn't reflect anything back out. So the opening behaves like the surface of a black body.
Clever. So you study the hole, but what about the emission part?
Right. Now, you heat the entire cavity, the walls of the box, to a very uniform, stable temperature, let's say 1,000 Kelvin.
Okay, the box is hot.
The inner walls of the cavity are constantly emitting thermal radiation because they're hot. They're also absorbing radiation from other parts of the wall. Inside that cavity, the radiation field comes into perfect thermal equilibrium with the walls.
A stable state of radiation bouncing around inside.
Yes. And now, the small amount of that internal radiation that happens to be heading in the right direction to escape out through that tiny hole, that escaping radiation is a very, very close approximation to the thermal radiation that a true theoretical black body would emit at that same temperature, 1,000 K in our example.
So you measure the light coming out of the hole to study black body emission. What's so special about that light, that radiation?
This is where the black body becomes absolutely fundamental in physics history. The spectrum of the radiation emitted by a black body, meaning how the intensity of the radiation is distributed across all the different wavelengths or frequencies, turns out to depend only on its absolute temperature.
Only temperature, not what the box is made of or its shape or anything else.
Nope, just temperature. Doesn't matter if the cavity is made of copper or ceramic, if it's a sphere or a cube. If it's at the 1,000 K, the radiation escaping the hole will have exactly the same characteristic spectrum. This universal temperature-only dependence makes it the perfect system for studying the fundamental link between heat and light.
The spectrum, you mean like how much energy comes out as infrared, how much is red light, how much is blue light, ultraviolet, and so on?
Precisely. If you use a detector that can measure intensity at different wavelengths, you can plot it out. The material shows this in figure 1.6, these characteristic black body curves. For any given temperature, you see the intensity starts at 0 for 0 wavelength.
Yeah.
It rises smoothly up to a peak intensity at a specific wavelength.
Okay, a maximum point.
And then it smoothly decreases again as the wavelengths get longer and longer, eventually tailing off.
And those curves look different for different temperatures.
Dramatically different. Two main things happen as you increase the black body's temperature. First, the total amount of energy radiated, which is like the total area under that curve, increases very, very rapidly. Hotter things radiate way more energy overall.
Okay, more energy total. What's the second thing?
The second thing is that the wavelength where the curve reaches its peak intensity, we call that the peak wavelength, lambda max, shifts towards shorter wavelengths.
Shorter wavelengths, towards the blue end of the spectrum.
Exactly, towards blue, violet, and even ultraviolet if it gets hot enough.
Ah, so this is the science behind why things glow different colors when they get heated up.
This is exactly it. Think about heating a piece of metal. At room temperature, it's emitting infrared, but we can't see it. As you heat it, it gets hotter, the total radiation increases, and that peak wavelength starts to shift from the far infrared into the visible spectrum.
Okay, first it glows. Dull red.
Dull red, yeah. That's the peak, hitting the long wavelength end of visible light. Heat it more, the peak shifts further through orange, then yellow. Get it really hot, like a light bulb filament.
It looks white, or yellowish white.
Right, because the peak might be in the yellow or green, but it's now emitting significantly across all the visible colors: red, orange, yellow, green, blue, violet, and our eyes mix that all together as white light. If you get even hotter, the peak would move into the blue or UV, and it might look bluish white. Figure 1.6 shows this shift very clearly. The peaks move left, shorter, as T goes up.
That connection between temperature and the color of the emitted light is just fascinating. And these careful measurements of the black body spectrum, these curves, they led to some really important physical laws.
They absolutely did. The experimental data was crucial. It led directly to two key quantitative laws describing black body behavior. The first one deals with that peak wavelength shift. It's called Wien's displacement law.
Wien's displacement law. Okay, and this puts a number on how the peak shifts with temperature.
Exactly. Wilhelm Wien found, based on thermodynamic arguments and fitting the data, that the wavelength at which the emitted intensity is maximum is inversely proportional to the absolute temperature, T, of the black body.
Inversely proportional. So as one goes up, the other goes down.
Right. The formula is beautifully simple. Multiplied by T equals a constant, where B is known as Wien's displacement constant. The value given in the material is about 2.898 by 10 anna Kelvin.
Meter Kelvin. Okay, so if you double the absolute temperature, the peak wavelength gets cut in half.
Precisely. It shifts to much shorter wavelengths.
And this simple law is actually useful.
Incredibly useful.
Yeah.
As you hinted at before, astronomers use it all the time. They can carefully measure the spectrum of light coming from a distant star, find the wavelength where the intensity peaks.
And then use Wien's law to calculate the star's surface temperature.
Exactly. Even though the star is light years away. The source gives the sun as an example. Its peak emission wavelength is measured to be around 475 nanometers. Plug that into Wien's law. T, 2.898 by 10 Mk, 475 by 10 MREM, and you get a surface temperature of roughly 6101 gigakelvin.
Over 6,000 Kelvin, just from the color, essentially. Amazing. Even though you said the peak is 475 millimeter, which is kind of greenish blue, but the sun looks yellowy white to us.
Yeah, because while the peak is there, the sun is emitting so intensely across the whole visible spectrum that our eyes perceive the mixture as yellowish white. But the underlying peak location tells us the temperature via Wien's law.
Okay, that's Wien's law for the peak wavelength. What's the other major law that came from studying black bodies?
That's the Stefan-Boltzmann law, sometimes just called Stefan's law. This one tackles the total amount of energy radiated by a black body across all wavelengths combined, essentially, the area under those curves we saw.
Okay, the total power output.
Yes. It states that the total energy radiated per unit surface area, per unit time, which is a measure of power intensity, often called emissive power or radiant excidence, symbol E, is directly proportional to the fourth power of the black body's absolute temperature.
The fourth power. Not just proportional to temperature, but T to the power of 4.
T to the power of 4. This means temperature has an absolutely enormous influence on the total energy radiated.
Wow. So like if you double the absolute temperature,
the total energy radiated per square meter goes up by a factor of 2, which is 2 times 2 times 2 times 2.
16 times.
16 times more energy radiated. If you triple the absolute temperature, the radiated energy goes up by 3 hours.
3 times 3 is 9, times 3 is 27, times 3 is 81.
81 times more energy radiated. You see how rapidly it increases. This Tate dependence is incredibly powerful. It's why really hot things radiate energy away so incredibly effectively compared to merely warm things.
No wonder stars are so luminous. Their temperatures are huge.
Exactly. The formula is written as E, where E is the energy per unit area per second in watts per square meter. Key is the absolute temperature in Kelvin, and the Greek letter sigma is a fundamental physical constant called the Stefan-Boltzmann constant.
And it has a value.
Yes, it's approximately 5.67 by 10 watts per square meter per Kelvin to the fourth power.
W millicold.
Okay, so E gives the power per unit area. What if you want the total power from the whole object?
You just multiply by the total surface area A of the black body. So the total power radiated, P is P equals A.
Okay, so Wien's law tells us the color, peak wavelength, and Stefan-Boltzmann tells us the total brightness, total power radiated, for an ideal black body. But back to Leslie's cube. Real objects aren't perfect black bodies. That shiny face radiated much less than the black face. How do these laws apply to, well, everything else?
Great question. This brings us back to those concepts of emissivity and absorptivity we introduced briefly. For real surfaces, we need to modify the black body laws. Remember, emissivity, symbol, epsilon.
Yeah, it was like how good something is at emitting compared to a black body.
Exactly. It's defined as the ratio. The energy emitted per unit area by the real surface at a certain temperature, divided by the energy emitted per unit area by a black body at the exact same temperature. So for a perfect black body, the ratio is 1 divided by 1. Emissivity equals 1.
Perfect. And for any real surface, its emissivity will be somewhere between 0 and 1. A very poor emitter, like that polished silver surface, might have an emissivity close to 0, maybe 0.05 or something. A very good emitter, like the lamp-black surface, might have an emissivity close to 1, maybe 0.95 or higher. Most everyday objects are somewhere in between.
Okay. And what about absorptivity, alpha?
Absorptivity, A, is defined similarly but for absorption. It's the ratio of the radiant energy absorbed by a surface to the total radiant energy falling on it, incident upon it.
So for a black body, which absorbs everything, A equals 1.
Correct. And for real surfaces, E is also between 0 and 1. A highly reflective surface, like a mirror, absorbs very little, so it has a low absorptivity, close to 0. A dark, matte surface absorbs a lot, so it has high absorptivity, close to 1.
And you mentioned earlier there's a fundamental link between these two, emissivity and absorptivity for any given object.
Yes, there is, and it's described by Kirchhoff's law of thermal radiation. Gustav Kirchhoff figured this out. It states that for any object in thermal equilibrium with its surroundings, its emissivity at a given wavelength and temperature is exactly equal to its absorptivity at that same wavelength and temperature.
Always at equilibrium.
At thermal equilibrium, yes.
Mm-hmm.
This is a really crucial insight. It means that surfaces that are good at absorbing radiation are also necessarily good at emitting radiation.
Mm-hmm.
And surfaces that are poor absorbers, meaning they're good reflectors, are also necessarily poor emitters.
Ah! So that black t-shirt that gets really hot in the sun.
It's hot because it's a good absorber of the incoming solar radiation.
High.
Yeah.
And Kirchhoff's law says it must therefore also be a good emitter of its own thermal radiation. High.
Exactly. And the white t-shirt. It stays cooler because it's a poor absorber. It reflects most sunlight, low I.
Yeah.
And therefore, it must also be a poor emitter, low I.
So in sunlight, the difference in absorption of the sun's energy is the main reason the dark one gets hotter, even though it's actually better at radiating its own heat away once it gets hot.
That's a perfect way to put it. The absorption dominates in that scenario.
All right.
Okay, so now we know for surfaces in equilibrium, how do we use this with Stefan-Boltzmann's law for real objects?
Do we just multiply by the emissivity?
Pretty much.
Yeah.
Since a real surface only emits a fraction of what a black body would, the energy radiated per unit area per unit time for a real surface at temperature T is simply E equalistos.
Okay, just stick the A in front.
Yep. And the total power radiated by a real object with surface area A and emissivity, half dP equals SEO.
That seems straightforward enough. What about the net heat exchange, though? Like our cup of coffee cooling down, but now considering it's a real cup, not a black body.
We can adapt the Prevost idea using emissivity. Imagine our real object has surface area A, emissivity A, and temperature T. It's sitting in surroundings, like a room, that are at a uniform temperature T. The object is emitting radiation, according to P emitted A. At the same time, it's absorbing radiation from the surroundings. If we approximate the surroundings as behaving like a black body enclosure at temperature T, which is often a reasonable assumption for a small object in a large room, Then the intensity of radiation hitting the object from the surroundings is a store.
Right, the black body emission from the surroundings.
Now, how much of that incoming radiation does our object absorb? Its absorptivity is AT, and by Kirchhoff's law, AT. So the power it absorbs is AT incoming intensity.
Ah, okay. Power emitted is AT. Power absorbed is AST.
So the net rate at which the object loses energy by radiation is the difference. P net emitted, P stored.
Which is P net equals STS.
Exactly. And we usually factor that to write it neatly as P net T.
P net equals epsilon A sigma times T to the fourth minus T naught to the fourth.
That's the one. This formula is incredibly useful for calculating radiative heat loss or gain for real objects in real environments. It clearly shows the net exchange depends on the object's emissivity, its area, and importantly, the difference between the fourth powers of the object's temperature and the surroundings temperature.
The material gives a couple of worked examples using these. Maybe quickly walking through them will help cement it. There's one about a lamp filament.
Right. Example 1. It says we have a lamp filament at a high temperature, T equals 2450 Kelvin. Its surface area is tiny, A equals 1.0 by 10 square meters. And its emissivity is given as A equals 0.35. It asks for the power radiated.
So we use P ASTO.
Exactly. Just plug in the numbers. P 0.35, 1.0 by 10 5.67 by 10 ASWH, or 2450 Kelvin.
Okay, multiply all that out. 2450 to the fourth power is going to be huge.
It is. When you calculate it, it comes out to approximately 55 watts.
55 watts from that tiny little filament.
Yeah, even though the area is small and the emissivity isn't super high, 0.35 is typical for tungsten, the incredibly high temperature, T, means it radiates a lot of power, 55 joules every second. That's why it glows so brightly and gets so hot.
Okay, that makes sense. The other example was about heat loss from a sheet.
Yes, example 2. This one uses the net radiation formula. We have a thin, rectangular sheet, dimensions 0.1 meters by 0.2 meters. Its temperature is T equals 600 degrees Celsius, and its emissivity is air equals 0.8. It's inside an enclosure that's at T arrow 23 degrees Celsius. We need the net rate of heat loss.
First step, convert temperatures to Kelvin, right? Always absolute temperature for these laws.
Crucial step. T is 600 plus 273 yields 873 K. And T arrow plus 23 plus 296 K.
And the area, T arrow 0.1 meters to 0.67 1 and 10 arrow old Leibniz square meters.
Right. Now we plug these into P net, a loss to TO.
So P net 0.8.02 meters, 5.67 by 10 arrow, 873 K, 296 T.
You need to calculate those T terms. 873 arrows is large, 296 arrow is much smaller.
And the result is?
The calculation yields a net heat loss rate of approximately 296 watts.
Nearly 300 watts. So even though this sheet is much cooler than the lamp filament, 873K versus 2450K, it's losing a lot more heat overall. Why?
Well, two main reasons here. Its surface area, 0.02 meters 2, is much larger than the filament's 10 years, and its emissivity, 0.8, is significantly higher than the filament's 0.35. So even though the T term is smaller, the A and A terms are much larger, leading to a greater net power loss in this case. Plus, the temperature difference between the object and surroundings, TT, is substantial.
These examples really drive home how the different factors in the formulas play out in real calculations. Okay, so we've got the properties, the factors, the ideal black body model, and the laws, Wien's, Stefan-Boltzmann, Kirchhoff's, that describe both ideal and real radiation, but explaining the exact shape of that black body spectrum curve, the one in figure 1.6, that turned out to be a massive headache for classical physics, didn't it?
Oh, it was more than a headache. It was full-blown crisis. Towards the end of the 19th century, physicists felt they had a pretty solid handle on the world with Newton's mechanics, Maxwell's electromagnetism, and thermodynamics. They fully expected that these well-established classical theories should be able to predict the shape of the blackbody radiation curve from first principles.
But they couldn't.
They couldn't. No matter how they tried, the classical predictions just didn't match the experimental results across the whole range of wavelengths.
How did the attempts go wrong? What did classical physics predict?
Well, there were mainly two significant classical attempts, and they failed in opposite ways, interestingly. We mentioned Wien's work earlier. He developed a formula, partly based on thermodynamic reasoning, but also fitted to experimental data. His formula actually worked reasonably well for the short wavelength, high-frequency part of the spectrum. It got the peak location roughly right, leading to his displacement law, and predicted the intensity correctly dropping off towards zero at very short wavelengths.
Okay, so good for short wavelengths.
But his formula completely failed at longer wavelengths. It predicted the intensity would fall off much too quickly compared to what was measured experimentally.
So good on one side of the peak, bad on the other. What was the other attempt?
The other major effort was by Lord Rayleigh, later refined by Sir James Jeans. Their approach, the Rayleigh-Jeans law, was derived rigorously from classical statistical mechanics, equipartition theorem, and classical electromagnetism, treating the radiation in the cavity as standing waves.
Sounds solid theoretically. How did it compare to the data?
It worked beautifully, but only for the long wavelength, low-frequency part of the spectrum. It matched the experimental curve almost perfectly out there.
Okay, so Wien worked for short wavelengths, Rayleigh-Jeans worked for long wavelengths. What was the problem?
The problem was what Rayleigh-Jeans predicted for short wavelengths. As they calculated the energy distribution for higher and higher frequencies, shorter and shorter wavelengths, their formula predicted that the intensity of the emitted radiation should just keep increasing, heading towards infinity.
Infinite energy at short wavelengths. That can't be right. Objects would radiate infinite energy.
Exactly. It was a physically absurd result. This glaring contradiction between the classical prediction and the clear experimental evidence, which showed the intensity peaking and then decreasing at short wavelengths, became famously known as the ultraviolet catastrophe.
The ultraviolet catastrophe. Wow, what a name for a spectacular failure of a theory.
It really was. Figure 1.7 in the material shows it perfectly. You see the experimental data curve, solid line. Wien's formula, dashed line, matches it okay on the left, short luck, but fails on the right. Rayleigh-Jeans's formula, dotted line, matches beautifully on the right, long luck, but then disastrously shoots upwards towards infinity on the left, in the ultraviolet region.
So classical physics, the foundation of everything they knew, simply could not explain something as fundamental as the light coming from a simple hot object. It must have been deeply unsettling.
It was. It clearly signaled that something was profoundly wrong, or at least incomplete, with the classical understanding of how energy works at the microscopic level, especially concerning the interaction between matter, the oscillators in the cavity walls, and electromagnetic radiation. The black body spectrum became puzzle number one.
And this deep puzzle, this crisis, is what set the stage for Max Planck, right? Around 1900.
Yes, exactly. Max Planck, a German physicist, was obsessed with solving this black body problem. He knew the experimental curves were reliable. He wanted a single formula that could reproduce the entire curve from end to end perfectly.
Did he just try to combine the Wien and Rayleigh-Jeans formulas somehow?
He did play around with things like that, trying to interpolate between them, but it felt unsatisfactory, like just a mathematical trick without a real physical reason behind it. Then, in what he later described as an act of desperation, he decided to try something truly radical, just to see if he could mathematically derive a formula that worked.
And this radical idea was about the energy itself, not just the waves.
Precisely. To make the math work out and produce a formula that perfectly matched the experimental data, Planck found he had to make a shocking assumption, one that flew in the face of all classical physics. He had to assume that the energy of the microscopic oscillators inside the cavity walls, the little vibrating things emitting and absorbing the radiation, could not just have any arbitrary value. Their energy was restricted. It had to come in discrete chunks. Energy, he proposed, was quantized.
Quantized, meaning it can only exist in specific amounts, like steps on a staircase, not a smooth ramp.
Exactly like steps on a staircase. He proposed that the energy E of one of these oscillators vibrating at a particular frequency couldn't be just anything. It could only be 0, or a specific minimum chunk of energy, or 2 times that chunk, or 3 times, and so on. It had to be an integer multiple, n equals 0, 1, 2, 3, of a fundamental energy unit. And crucially, that fundamental energy unit was proportional to the oscillator's frequency.
So the size of the energy step depends on the frequency.
Yes. His formula was E equals NHF, where n is the integer, the step number if you like, f is the frequency of the oscillator, and h was a brand new constant he had to introduce to make the units work out. We now call it Planck's constant.
Planck's constant, h, the value is tiny, something like 6.634 by 10 Joule seconds.
Incredibly tiny, yes, but it turned out to be one of the most fundamental constants in the universe. It sets the scale for this quantum behavior. Now, Planck further proposed that when an oscillator emitted or absorbed radiation, it wasn't a continuous process. It had to jump from one allowed energy level, say level n, to another allowed level, say N1.
It jumps down a step to emit energy.
Yes, and the energy difference between those two steps, NHF, NH1HF, was precisely the energy carried away by the emitted electromagnetic radiation.
Yeah.
So radiation wasn't emitted continuously, but in discrete packets or quanta, each with energy E equals HF.
A quantum of energy, E equals HF. Is that the photon?
That's exactly what it is. This idea, born from Planck's attempt to mathematically model the black-body oscillators, was the very birth of the photon concept. The idea that light and other electromagnetic radiation actually behaves like it's made of particles, or energy packets, in addition to behaving like waves. Figure 1.8 in the material tries to illustrate this, showing discrete energy levels and an electron jumping down, emitting a photon with energy hf.
So the whole quantum revolution started because Planck needed energy to come in steps to explain the light from a hot box.
Pretty much. It was this radical, initially quite uncomfortable assumption of quantized energy levels, EQF, and quantized emission absorption that allowed Planck to derive his famous black-body radiation formula, equation 3 in the notes. And the incredible thing was, his formula perfectly matched the experimental data across the entire spectrum for all temperatures. It predicted the peak, the fall-off on both sides, everything. As figure 1.9 shows, Planck's law nailed it where Wien and Rayleigh-Jeans failed.
It solved the ultraviolet catastrophe, too.
Yeah, it did, naturally. By linking the energy quanta to frequency, it meant that emitting very high frequency, short wavelength radiation, required very large energy jumps, large packets of energy. At a given temperature, the oscillator simply didn't have enough thermal energy, on average, to make those huge jumps very often. So the probability of emitting high-frequency quanta became very low, suppressing the radiation intensity of short wavelengths exactly as observed and preventing the infinite energy prediction.
Wow. So a seemingly very specific problem explaining the color and brightness of heat radiation forced physics to accept that energy isn't continuous at the micro level. It comes in packets. And that idea just snowballed into all of quantum mechanics.
It really did. Planck's discovery in 1900 is widely considered the birth certificate of quantum physics. It was a profound paradigm shift, driven entirely by the need to explain this one persistent experimental puzzle, the black body spectrum. It's a fantastic example of how digging deep into a fundamental observation can completely revolutionize our understanding of the universe.
Okay, so let's bring this all back home. We started with just feeling the sun's warmth, and we've ended up talking about energy quanta and the birth of modern physics. What are the key takeaways for understanding thermal radiation in our world?
I think the key things are, thermal radiation is this fundamental way energy moves via electromagnetic waves, driven purely by an object's temperature. It doesn't need a medium, it travels at light speed, and its intensity drops with distance.
Right. And how much is radiated depends crucially on temperature. That Tail law is huge, but also on the surface area and the nature of the surface, its emissivity. Dark, matte things are good emitters. Shiny things are poor emitters.
Exactly. And remember Prevost's idea. Everything is always radiating and absorbing. What matters is the net exchange, which drives objects towards thermal equilibrium with their surroundings, where emission balances absorption. ATO feet, thanks to Kirchhoff.
We also met the ideal black body, the perfect absorber and emitter, which acts as the theoretical benchmark, whose radiation spectrum depends only on temperature.
And studying that spectrum led to Wien's law, peak wavelength versus temperature, and the Stefan-Boltzmann law, total power versus T.
And ultimately, the failure of classical physics to explain that spectrum forced Planck to introduce the revolutionary idea of energy quantization, giving birth to the photon concept in quantum mechanics.
It's a story that connects everyday experiences like warmth and color to the deepest levels of physics. And understanding these principles is vital everywhere. Designing insulation, understanding stars, building night vision cameras, climate modeling.
It really is everywhere once you start looking through this lens, that constant, invisible flow of energy.
Which brings us to a final thought for you to ponder.
Yeah.
Consider again that energy from the sun. It crosses 93 million miles of empty space, purely as thermal radiation, governed by the very principles and laws we've discussed, laws whose ultimate explanation lies in Planck's quantum hypothesis.
Yeah.
That incoming energy doesn't just warm us. It drives photosynthesis, powers our weather systems, evaporates water, creates winds. It's the engine of life and climate on Earth. This silent, invisible stream of energy packets, whose nature baffled scientists until they embraced the quantum world, is fundamentally shaping our planet and our existence every single moment. How does really thinking about this quantum connection underlying the sunlight change how you perceive the simple warmth on your face or the light filling a room?